So this presentation is about the cpuidle driver, generic cpuidle driver. So it's not magic. I mean, it's not a driver doing everything for PM, but it's a glue between a description in a DT and the low PM, low level code. So the purpose of this presentation is to explain how this driver has been written and how to implement your own driver using this new generic framework. So the legacy drivers, we had a lot of problems with them that were very difficult to maintain, and the first cpuidle driver arrives with one board, and then the next stock vendor created another driver doing a copy paste of the first one, and the third one do a copy paste of the second one, and then that end up with different driver spread across the tree, and with duplicated code, and that was very hard to maintain, because when you try to do some modification in one driver to factor out the code, as the drivers are spread across the tree, they fall under different maintenance tree umbrella, and that's it's very difficult to track changes to have a consistent driver. So also we have the driver was very tied with the low level code, and we had also static table defined directly into the driver. So we try to improve this situation, and we did a lot of changes into the driver. So consolidate all the code, put the common code into the cpuidle generic framework, and we used, in order to prevent to have in the driver cpuidle directory inclusion directly in the ARM Mac something, we use the platform driver data, the private field in the platform driver structure. We use that to pass the ops for the PM, for the callbacks to enter the different idle states. So at the end, when we had the Linux kernel 3.0, there were 0 driver in this directory. And right now, in the Linux version 4.0, we have 14 driver in this directory. So it's much more easier to maintain these drivers, because we can just have one place and say, okay, I maintain this place. So everyone, when are sending patches, are sending the patches to a single person. But what happened is the platform data. So I don't know if everyone here knows what is the platform data. It's a field in a driver model. It's a field we have one structure, which is the device, one structure, which is the driver, and then we pass the data from the device to the driver through a generic structure. And this data is the platform data. So that means we had to create a device for a cpuidle driver. So that raised some discussion around the cpuidle driver is not a device, and that shouldn't fall in this area. And moreover, the drawback of this approach is we have to load all the drivers in a single Z image. We have to load all the drivers, and then that consumes more memory. So we have drivers in memory for nothing, as there will just be one will be enabled by one device. So in the meantime appears the ARM64 generic driver based on the PSCI. So it's quite simple, because the PSCI gives the callbacks to call the firmware PM sleep function. And then we generalize this driver to create a generic ARM cpuidle driver where its purpose is to use in the device tree the idle state description, and on the other side we have the low-level PM ops, which are the sleep functions in order to enter retention, core sleep, or cluster sleep. The generic ARM cpuidle ARM driver will use the information you will find here to initialize this. It will do the glue and then use the cpuidle framework. So thanks to that, we split out what is really, really Arch-specific, and we also give the opportunity to describe these states in the device tree. So if you want to create a driver, you have to first describe the idle states. In the DT, you have the name of your idle state, the compatible string, which is very important. We will see later how the cpuidle driver will use this string to do the connection between what is described here and the low-level PM code. We enter the latencies. So the cpuidle driver will use this information to create a driver dynamically at boot time and initialize the different idle states with that. But what will be missing for the cpuidle driver is the callbacks. Then in the device tree for the CPU definition, you refer to the cpuidle state you defined previously. Thanks to that, and then on the other side, we have the low-level PM ops. So I will just skip this part because it's quite simple. It's the same when you are in the ARM64 and you implement the PSCI and you use the PSCI for cpuidle. Then, well, there is nothing really different from one board to another board. But what applies here, what I will describe with this approach is the same here, except that instead of having PSCI and the CPU operation are different, the structure CPU operation is different because doing more things with ARM64. On ARM, we will just use cpuidle ops because CPU plugging is handled in a different place. So first of all, we have the cpuidle ops with two functions, which is the init and the suspend. The initialization is declared with a macro. So this macro is special. It's a macro allowing to add element in an array, but when the init section is finished, it's unloaded from memory. So that allows to have a lot of boards declaring each of them declaring this method. This method is added into an array, and then when just one element of this array will be used at init time to initialize the cpuidle ops, then all the array will be unloaded from memory. This cpuidle ops, so there is the suspend and the init, and here we see that we have one string here, and this string will be describing the compatible for the DT. And we specify the cpuidle ops. On the other side, we have a matching table. This matching table gives the name of the idle state we will find in the DT. and we associate with the idle state the callback. So we fill the hole which was empty when we created the driver. We fill one idle state, added the different latencies, but the callback to enter this idle state was missing. This description allows to add this missing information, which is the callback to enter the idle state, name with that. So it's very important to understand that the cpuidle driver, generic cpuidle driver, allows to sign the contract between the low-level PM code and the device tree description. So the ARM cpuidle driver itself has has a default WFI function. It parses the DT, fill the driver with different idle states, and call the different ops. So we have init and suspend. We will come back to suspend just after. So here, to remind, is your CPU description. So you have the compatible here, saying Qualcomm Cree, and we have enable method. This enable method has a name, which is this one. On ARM64, this enable method allows to do CPU hot plug also. This information is also used to boot the secondary CPUs. And in the low-level PM code, we have this information. Okay, so the generic ARM driver is looking up for this enable method and then find in the array, global array, this information and takes the cpuidle ops and calls from there the init. So that's what I said. Then we have the suspend. The suspend, we have usually in the old cpuidle driver, we see for each idle state, we have a different enter function. Now we have just always the same function, which is the ARM enter idle state, with a default section. When the index is 0, we call just WFI. Otherwise, we call cpuidle suspend, which is the suspend ops we found before. There is some code, the command code is inside this function, and then the ops is called from there. And we pass the index. The index is the number of the idle state we want to enter in. So the low-level PM code, we look at this index, and it knows the meaning of this index. If it's 1, it could say, okay, index 1 means I want just to do retention. If it's 2, that means I want to do core power down. If it's 3, then I want to do cluster power down. So it's up to the low-level PM code to figure out what to do with the index passed in parameter. Oh, was a fast presentation. So as a conclusion, everything is self-contained. Thanks to this approach, everything is self-contained. So really, you don't have to care about pulling code from cpuidle inside of PM code. You don't have to accept some header to initialize and so on. The cpuidle driver don't have to take care about the low-level PM code. It can just do what is generic. It's flexible because you can describe the different idle state directly into the DT. You can have for different board, different latencies, but with the same cpuidle driver, and the device tree allows you to have some flexibilities without changing the kernel itself. And it's simple because you don't have to take care of the cpuidle driver itself. You just focus on your low-level PM callbacks. But there is some restriction at the moment. The first restriction is for the big little, for example, architecture, we need a support which is called the multiple driver support. So usually what is, you have for one cluster where you have one cpuidle driver, and for the other cluster you have a different cpuidle driver. And the generic cpuidle driver does not use that. It does not detect if the idle states are different, so it will use the same driver for all the CPUs. So what we are now trying to achieve in a nice way is to have the cpuidle ARM driver to automatically detect that we are using different CPU with different idle states, and then create a different driver. So the driver, so the CPU, when the CPU will enter idle, it will use its own driver. Each CPU will use its own driver. Another thing is in the DT we have a flag telling that we are shutting down the local timer. So right now it's not very nice. It's put there, but what we want to do is to describe that with the power domains. Then when you power down, you make this local timer to belong to the CPU power domain. So this information can be used saying that, okay, if I shut down this CPU, then that will shut down also the timer. And the cpuidle framework can use this information to tell the time framework to switch to another timer, a backup timer, and switch back to the local timer when the CPU is woken up. This work is work in progress. There are people working here to have the sockiling and introducing generic power domain for CPUs. So that's the next step. At the moment, there is one proposition here to have the multiple driver support for the cpuidle driver. So the question is, today we compile the kernel with multiple driver support. That means even if we have the same driver for all the CPUs, that means we will have one driver per CPU for different instances of the same driver for each CPU. Or if we don't enable the multiple driver support, then we have to handle that directly into the driver itself to detect if we are big, if we are little, but that complexifies a lot the simple driver we wanted to do. So there is discussion around. Lorenzo is someone from ARM who did the ARM64, this approach for ARM64. And Lina here from Qualcomm did the first driver based on the changes I did for the ARM64 to generalize that for the ARM v7, the ARM32. Okay, I finished presentation. Was it clear, or you were expecting something more? What? Do you have questions?
Is it all upstream now?
Yes, it's upstream. Fox.
I saw there are some multiple driver. What does that mean? Do you mean one of device has support multiple driver?
Can you repeat again?
The previous slides you can get back. You can get back the slides
Previous slide.
Yeah, on the previous slide. Okay, sorry.
Multiple driver support via DT definition.
Yeah.
So is that you can use several drivers on just one device.
Yeah.
Why? Why you need multiple driver?
Because if you can have different CPUs on your system. You can have big and you can have little. Okay, that's not that's not the only use case for the multiple driver, but usually it's that. So the driver is not designed to have to know in which CPU is running on and what to do. So instead of doing the code where we will looking, okay, I'm on the little, so I will call this function. Oh no, I'm on the big, then I will call this function. Instead of that, we just create one driver. In this driver, there is a CPU mask saying, okay, this driver applies to this CPU, this CPU, this CPU, this CPU. And we have another driver with a CPU mask saying we apply to the four other CPUs. So when you are in the dynamic of entering idle, the callback is just the CPU from the CPU context will just call get driver and have its own PM callback to go to the idle state.
Okay. Also, that means each CPU type will have a different driver. This means a driver for bigger and another for little.
Yeah. Each one has its own driver.
Okay.
So you, for example, you have four little and 4 bigs. Then you have one driver for the 4 little and one driver for the 4 bigs. They're just a ref counting to the same driver. So you have 2 drivers for 2 clusters.
Okay, thank you.
You're welcome.
According to my understanding, the difference between the little core and the big core should be covered by the entrance latency from the DT definition. But I think all the driver and all the enter paths for the different cores should be same. I think the difference should be covered by the CPU idle governor. They can tell the enter latency for the little core is reached, and this core should be entered for this level of CPU idle.
Yeah, but for the idle states are per driver. So you cannot, at the moment, well, that's one of consolidation appeared 3 years ago. Before you had per CPU, the idle state per CPU. That was consolidated because that was always the same idle states. So that was consolidated, and we have just one driver and a table of idle states, which are the same for all the CPUs. So you can't create different idle state table for different CPU. The only way to do that, you have to add multiple driver support and create a new driver with new idle states. In the DT you cannot rely on the target residency and exit latency, because for some CPUs which are different, they have different PM callbacks, but they have the same latencies. But what you can do, as you have 2 different descriptions for the idle states belonging to different CPUs, you can detect that and then create a new driver. That was the proposition Lorenzo did recently.
Yes, thank you. And for the PM callbacks, you just mentioned is that, from my understanding, we just need to focus on the PM callbacks within the PSI, within the trust zone, and no need to care about the framework or the driver on the kernel work.
That's correct. Yes. So everything in the PM, just, yeah.
Yes. So is this framework compatible with the general power domain for the CPU idle?
No, not yet. I wish. I wish. That's part of the next steps.
So maybe if the Linux patch is merged, the driver should be modified.
Yeah, it will be modified, but it shouldn't break the older drivers.
Okay, thank you.
So when you're talking about the multiple driver support, you keep on bringing up big little, but is there going to be support for more than just a big little cluster, big medium little, anything like that as well?
So I'm not sure I got your question. You're saying that say it again.
So basically, you say big and little support.
Yeah.
And this is the reason for having the multiple driver in order to to support these two separate clusters.
Yes.
So I'm asking, are you limiting it just to the two, or do you envision some expandability if somebody adds another processor type besides just big and little?
I didn't find yet a situation where we need different cpuidle driver except for the big little. But recently I saw an architecture, I won't say the name of but they have a CPU 0 which is in a always power on domain, which cannot go to either. It has just W5, and then he has the 3 other CPUs which are able to go to power down themselves. So in this case, we have one CPU which has, we can say just one, has no CPU idle driver at all, or needs one stage just for WFI, and maybe can have to do some work for the other CPUs. That happens also. That was the only case I found where we need two CPU idle drivers. You had a question, no?
I have a question to Kevin as well. Kevin, once we represent CPU as a generic power domain, will we be using CPU idle framework as well while idling? What is the plan?
I don't know. It's not, for me, it's not terribly clear where the boundary is going to end up between GenPD governors and CPU idle governors and stuff. I think that's all kind of in the implementation details, but yeah, for that level of detail, I just don't know yet. I mean, whether it's inside a CPU idle governor or inside a GenPD, we need the exact functionality that where this is going. So, yeah, sorry, I don't know.
Questions? No? No? I have a question. What are your expectations when you come to this presentation, when we were talking about the cpuidle driver? Is what you were expecting, or do you have the need to have something more technical, explaining the subtleties of the cpuidle driver themselves, the PM? What kind of information that will help me for the next Connect to do a presentation, a more technical presentation, if this is what you want?
Thank you. Just answer your question. So from my point of view, I think it's better to have some real demo for the CPU, with the CPU driver with big and little, and maybe some use case to show up, to see how much power we can save with the CPU idle driver, maybe some other PM related stuff. That's it.
Okay.
Thank you.
something more technical? Do you prefer next time? Explaining really the low level side?
You was concentrated on implementation, but about it will be good to see or to know an idea or about this, something about design. I worked on a previous cpuidle for ARM64, and it will be interesting for me. There was a different framework.
It actually tells me that something has changed in this space and I have to look at it again. I thought I'm interested in more details in the code. So I think you were dead, like right on par.
Yeah, the answer is on the code. I agree. The problem of cpuidle is there is a lot of subtleties because we are in a particular situation, and maybe some people might want to have more technical details and wants to know what could be the pitfalls when implementing a cpuidle driver. So that's what I'm interested in. If what level of details people might be interested in, because I did different presentation, but very detailed presentation and before, and I don't know if people might be expecting more coming. Well, if I have to resurrect this old presentation to explain that again or not. Okay. Thank you.